All right, I've had a request to do a Fred and Barney style question, and Jason and Steve did one up. So let's see if it's doable, first of all. It's a 1 kilometer track, is that right, Jason?
It was a 1 kilometer track.
Okay, so as soon as you see something like this where two objects have to, a guy's catching someone or they're colliding, you have to think the positions have to be the same, right? So in this case here, we've got Fred, he's traveling at a constant 10 kilometers an hour. Barney's accelerating at 2 kilometers per hour squared towards him, and the whole track is 1 kilometer long. Now, Ryan and Jason, I got a bit of a problem. How am I going to handle that this is in hours, and clearly that this collision is going to happen in the unit of seconds?
That's why I have proved it. So.
Okay, so what should we do to fix this maybe?
How
How about we just do this? Can we just change the question?
Yeah.
Change that to meters per second, and change this to meters per second squared. Does that work for you?
Yeah.
Okay, so if you want to copy down this question, you can. This is a made-up one that these guys came up with here. And let's work through this together. All right, this is the acceleration of Barney over here, right? So they collide when their positions are the same, right? And so the position, they collide when their positions are the same. So the position of Fred at the start is 0, and the position of Barney at the start is plus 1,000 in meters, right?
I think, okay, so
They're going together, yes, they're playing chicken. Now, their positions are going to change throughout the time frame here, right? So the position of Fred, PF, is going to be equal to his displacement, which in this case here, because he's traveling at a constant velocity, is V times T, right? So that's going to be equal to 10T, right? The position of Fred is 10 times T. Position of Fred is 10 times T. Kaylana, are you watching this? Should. Okay, I'm just making sure. The position of Barney is going to be 1,000 minus his displacement, right? Or should I say plus his displacement and just make his displacement negative? That might be better. 1,000 plus his displacement, which is going to be, what do I have? I have his acceleration. So that's going to be VIT plus 1/2 AT squared. Right? The displacement is VIT plus 1/2 AT squared. We don't know the time. We do know the acceleration. Do we know the initial velocity? We can only assume it's 0. We have to assume he's starting from rest. So the position of Barney is going to be 1,000 plus the VIT gives us
0.
0. 1/2, I'm going to say his acceleration is -2 because it's towards the left. Yeah, well, I'm going to get to that. Okay, don't just assume it. So it's 1,000, 1/2 of minus 2 is going to be 1,000 minus t squared, right? The position of Barney is defined by the function 1,000 minus t squared.
Why do you have 1,000 plus VIT plus 1/2?
Displacement formula is, Jason, VIT plus 1/2 AT squared, right? His position is starting at 1,000 plus his displacement. And his displacement eventually works out to be minus t squared. Because you conveniently pick 2 as your acceleration. Okay, so when do they collide? When their positions are the same, which is when 10t is equal to 1,000 minus t squared. We have ourselves a quadratic here. So t squared plus 10t minus 1,000 equals 0. Is that factorable? It will definitely go into the quadratic. Is it factorable though? Are there factors of 1,000 multiply? They told me in the question that the tract was 1 kilometer long. They said in the question that it was 1,000 kilometers, or kilometer long, or 1,000 meters. I can't think of anything, so we're going to have to use quadratic formula, right?
This one's given to us, right? Or maybe I'm
What do you mean?
quadratic.
I ain't giving you nothing.
Okay.
Make sure you got the correct quadratic formula on your cheat sheet. Minus b plus or minus square root b squared minus 4ac all over 2a. And before I forget, back to the question here. So minus b is going to be minus 10 plus or minus the square root b squared. B is 10 minus 4 times a is 1 times c is minus 1,000 all over 2 times a. 2 times 1 are just 2. Minus 10, plus or minus. 10 squared is 100. 4 times 1 is 4, times 1,000 is going to be plus 4,000. All over 2. Now, time has to be positive, right? So the only way for time to be positive, because the bottom is positive, that means the top has to be positive as well, right? So it's going to be minus 10 plus or minus the square root of, well, let's do square root of 4,100 right now. Can someone do that for me? Square root 4,100?
I'll do it right now. 64?
64? Is that right? Okay. So 10 plus or minus 64. To get positive time, because the bottom is positive, that means the top has to be also positive. So what's going to give me positive? Positive plus 64 or minus 64? Plus. So minus 10 plus 64 is 54 over 2, 25, 26, 27. 27 seconds, they will be in the same position.
So the question was
I don't know, Jason wrote the question. I think he asked, where do they collide, right?
yeah.
So I found out the time. How do I figure out where that happens? Well, I have 2 formulas for where. One is Fred's and one is
Oh, so you
Barney's, right? So this is going to be
27 meters.
10 times 27, 200 at position 270. Should you get position 270 out of this as well? I thought when they collide, they were in the same place.
Wouldn't it be like 730 or 7? Yeah. He starts at 1,000. Goes at 1,000.
I'm going to do it down here in yellow, in red. 1,000 minus 27 squared. Go ahead. What's 1,000 minus 27 squared?
No, it's not. Like, yeah.
What's 27 squared? Should be the same. What's 27 squared? 626, 700, what? 1 meter difference? Why is that, do you think?
I rounded that one number, 64.
Oh,
64 points.
which number?
Yeah, further.
Oh, right here, yeah.
We only have to find one answer, right, for where, because then the other one should
They should be, they have to be the same, yeah? You could check to see if they're the same by doing that.
So the
we
question,
have to check.
No,
so you could have put the question as like, how long would it have taken for them to
27 seconds, yeah. Jason asked where, so it's one more step, that's all right. And yeah, you're right, Steve, the only rounding that we did anywhere was that square root right there, right? So that's why. Yeah. I've been asked to go through these graph ones. So this is the velocity time graph, and you are to construct a dt graph. And I get that these are hard. I really do. Okay? You just got to think through them, and there's gonna be bits and pieces, right? They are really hard to redraw on graph paper. They just are. So when the velocity is going from 0 to some number, that means that it's this object, whatever it is, track star, or who cares, they are speeding up in the positive direction. So speeding up means curved, right? Speeding up means curved. Yeah, it's the one, it's this one right here. The one you just got back. This is the sign that you just got back. So right here is that. See, that's the one I'm doing right now. The one that you only got a half on. Yeah, 2.5, sorry.
I got you.
I don't know, but I think it is for sure. Yeah. I had at least 4 people in my morning grade 11 physics class that elected to do their first test without a study sheet. That's one word for it. Foolish might be a better word, right? It's not very smart. Okay, so anyways, here the velocity is doing what? Constant speed, which means the displacement has to be straight. In fact, this has gone from 0 to like 1, 2, 3, 4. This means that the slope is the same. The slope down here is the same that it was right here, right? In other words, this has to be a straight line at the same steepness, right? It's speeding up until it gets to some speed. Speeding up, and when it gets to that speed, it maintains that steepness, right? Okay, then the velocity goes back down to 0. Does that mean that it then goes back down to a displacement of 0? No, it just means that it stops. Right? So now the D has to do what? It has to level off. So it continues to curve up, and then it levels off. Now, already I've done what? Like, I've screwed up, because this 0 right here should be at the same time that this becomes flat. It's almost impossible to draw it right underneath like that on a grid. It's practically impossible. Okay? And I don't care about that. Okay? So like, I mean, what I really need to do here is I need to like scale this down, right, to make it match the time. It's hard to do, I get that. Okay, so now it's at 0, and now it's doing what here? The velocity is increasing negatively, so the object is backing up. And a lot of you had this, you just didn't go high enough. It's backing up, right? Does it go back down to d of z equal to 0? No, not necessarily. In fact, the only way to really check would be to find the displacement there, find the displacement there, find the displacement there, find the displacement there, and then you could tell what number it's at, right? But it certainly does not go past the origin, because this negative is not even close to this positive. You'll notice that it goes back to 0, right? It goes back to 0, which means that this thing has to flatten out. And then it speeds back up in the opposite direction and then maintains a constant speed. So it speeds back up and then maintains a constant speed. Hard to draw, hard to mark too, by the way. Because you got to sort of...
So can you explain to us, like, why it doesn't go to 0 on the DP graph after, like, it starts putting back down again? Like where it started turning, like you used a red marker there.
Yeah.
Why didn't you just keep going back down to 0?
Why would you want to go all the way down to 0?
I did.
But why?
Because it went past 0.
But this is 0 what, Steve? Not 0 position, 0 velocity. Velocity. Allow me to demonstrate just by walking here, right? Okay. Here I am in the middle of the room. I'll go this way, because I got more room. Jason, can you just pull that chair out of the way? Slide it away. Okay, so I'm here at the origin, right? Okay. And I'm going to go forward, I'm going to speed up. So I'm going to speed up. This will be my origin, this chair. I'm going to speed up, and then I'm going to maintain a constant speed, and then I'm going to slow down to 0. Have I gone back to my chair? I did the first 3 parts, right? These 3 parts is what I just did. I did this, I sped up, I maintained the constant speed, and then I went back to 0. But did I ever come back to the chair? How come? Does my velocity ever become negative? So can I ever back up? So it's speed up, constant speed, slow down to 0. And now it's 0. I'm at the part there where the graph crosses the x-axis of the dt graph, right? Then my velocity becomes negative, which means I go back towards the chair. I speed up at some point, and then I start slowing down, and I get to 0. But do I ever get to the chair? I might, but I'd have to be going for a long amount of time, wouldn't I, right? Then my velocity becomes positive, and back to a constant speed. And I end up way over here. Does that help, Steve? Does that help? There you go, yeah? Yeah? I got a few nods out there. Okay, good. Let's look at the next one then. Where did I put my... There we go. Okay, now the next one goes from dt to vt, which I think is actually easier.
It is.
Kind of something like that, right? Okay. So this is the dt and this is the vt. Okay, good luck, man. All right, so the dt graph is flat, which means it's stopped, right? Stopped, and the velocity is 0 to that point there. Then the dt goes back to 0. Remember, down here we are graphing the slope. What's the slope like here? The slope increases, and then it's going to a constant speed. So it's increasing. Actually, it's increasing, and then it's quickly going back to 0, right? So this is negative slope, negative, negative, 0. So this is slope down here. So negative, negative, negative reaches some maximum steepness, and then the slope goes back to 0. That kind of thing, right? Slope 0, slope negative, slope 0. Value is 0, very negative, back to 0.
Is that because it's kind of flat for a second, or is that?
I would say it's not even flat. I would say that it's curving this way and then it's curving that way. Okay? All right. Once it goes to 0, it stays at 0 for a while. Not my answer here. Actually, it's probably only briefly 0. Then it becomes positive. It's positive slope. We're graphing positive slope and increasing positive slope. Increasing positive slope. And then back to 0. Right? The slope is increasing, steeper and steeper. That's this black part here, and then back to 0 when it becomes flat. Does it stay flat for any period of time? Yes, it does. So it's briefly at 0 as it stays flat, and then here the slope becomes more and more negative, and so it goes down like that. Hard to mark, you guys, because if you make one mistake, then everything else changes, right? So yes, I have to sort of look at it and say, give it I'm going to subjectively give this to a 2 out of 3. Does that help, Manager? You were the one that asked for all this, right? Yeah? Okay, so those are your 2 answers there. Don't worry, there's not going to be like an entire 27 marks on this stuff. It's not going to happen. Did I show you this? I showed you this, right? That's exactly what's on the test.